We will now do section or chapter 3, section 1, and chapter 3 deals with what is known as linear regression. Linear regression deals with a situation where we want to see how two quantitative variables are related. So they've got to be numbers in essence. We've talked about the difference between quantitative and categorical variables. So it could be something like how is the amount of time someone spent studying for a test, how is that related to their score on a test? Both those things are quantitative variables. It can't be categorical. It can't be things like how is someone's race related to their religion, or how is someone's political party affiliation related to what state they're from. All those are categorical variables. So that's the first thing to check. Make sure the variable is quantitative. And we are going to, you got to be able to discuss the relationship you see between the two quantitative variables. You got to be able to show it using a scatter plot. And in the second section, we're going to create a model equation to be able to make predictions with it. But so let's look at this context and talk about the material that's in section 3.1. So it says a researcher at an automobile company wishes to study the relationship between the average speed in miles per hour that a particular car is driven over 100 miles and the gas mileage in miles per gallon that the car has for the 100 miles. And so first thing to notice, these are two quantitative variables. They are numbers, and it's paired data. You know, this car averaged 28 miles an hour and got 32 miles per gallon. This car averaged 32 miles per hour and got 31 miles per gallon. So this is regression data. So the first thing is this: the explanatory variable is in essence the x variable. It's the one that we think in the problem a change in it is somehow related to a change into the response variable, which is the y variable. So so the explanatory variable in this is going to be the mean speed in miles per hour. Always put the units. That's important. And then the response variable is what we think is responding to a change in the explanatory variable, and that is gas mileage. So that is gas mileage, and that is in miles per gallon. So certainly most of the time they'll list the explanatory one first and then the response one second, but not always. They don't have to do that, so that could be a tricky thing. You just have to ask yourself, which variable do I think is responding to a change in the other one? And that's going to be my response variable. So, and in this case, we think that the gas mileage is responding to a change in the speed. I mean, there could be other factors involved, certainly, in regards to things going on, but how fast you go is certainly appears to be affecting the gas mileage. So now the next thing we're going to do is we're going to draw a scatter plot, and a scatter plot is just a traditional XY plot of the data, and to describe the relationship, and that's really the main part of section 1 is just drawing that scatter plot and describe it. This is something that very frequently happens on the AP exam, many years, to draw a scatter plot and describe the relationship. And so that's what we're going to do. So with the scatter plot, make sure we're going to draw our axes, and so our explanatory variable traditionally goes on the horizontal axis, and so this is mean speed. So this is mean speed in miles per hour. Very important always to label and scale both axes. So that is labeling. And then the numbers are going from, let's see, I think the smallest one is 28 and it goes up to 67. So I'll just start with like 25 and 30, 35, 40, 45, 50, 55, 60, 65. All right, and then 70. Technically, you only have to write 2 numbers down to get credit for scaling. But anyway, and then we have gas mileage. So we have gas mileage, and that is in miles per gallon. Always put the units there. And so the gas mileage is going from, let's see, the highest 32, the lowest 14. So, if I started at like 10, let's say 10, so 15, 20, 25, 30, and then 35, and that'll take care of it. It doesn't have to be the neatest graph in the world, but it needs to be relatively neat. We just want to, in general, see what's happening with the data and being able to describe the relationship. So it doesn't have to be perfect. But anyway, so then I just plot these points. That's my x, just like x, y coordinates in algebra. So this would be 28, 32. So I go 28 and up to 32 is there, and I do that for all the points. 32, so 32, 31. And then 35, 31, and then let's see, 39, 29, so 39, 29, and then 42, 25, so 42, 25, and then 46, 26, and then 48, 22, so 48, 22, and then 52, 21, so 52, 21, 53, 19, so 53, 19, 56, 20, 56, 20, and then 59, 15, so 59, 15, 61, 16, 62, 15, and 67, 14, so 67, 14. And there we go. And so that's how you do a scatter plot. Now, I'm going to show you the shortcut to do that with your calculator, but most of the time it's really easiest just to do it by hand anyway. And a lot of times people get the calculator mixed up, so yes, you need to know how to do your calculator to do that, but the main thing is just to do it by hand. Now, it says to describe the relationship. Whenever you have linear regression data, this quantitative paired data like this, and you're asked to describe it, here's what you have to do. There's certain things you have to say, and it follows the DOFS acronym. DOFS acronym. You have to state its direction. Okay? In what direction is it going? Is it positive? Is it positive? Is it negative? Or is it just randomly scattered? Randomly scattered. And we'll look at some example of these things. Positive means, in general, it's going up from left to right. It's going up from left to right. Negative means, in general, it's going down from left to right. So that would be the case here. That would be the case here. That was the first thing you'd say, is there's a negative relationship going on here. The next thing is you have to state, are there any outliers? Outliers are way above or way below the data. They are outside the pattern of the other points. So in general, so they are way above or below the pattern of points. In this case, there's a pretty linear pattern. So a point like way up here would be an outlier. Way down here, it's not in the x direction. So if someone's average driving speed was 90 miles an hour, that wouldn't necessarily be an outlier, okay, because it's going to be close to our line that we're going to draw. We'll talk about that, but just an outlier is way above or way below the line. If it differed a lot in the x direction, if someone did average 90 miles an hour, all right, then we would call that an influential point. So keep that in mind. All right, the F stands for form. So is it linear, or does it show a noticeable curve? Noticeable curve. Now, linear doesn't mean that it's on a perfect straight line. You can have some scatter about that line. But linear basically means there's not some sort of noticeable curve, like some sort of parabola or some sort of exponential sort of thing, which later in the year we'll deal with that situation. But so is it linear or not? And then lastly, how strong it is, the strength. All right, how tightly packed is it to your graph, so to speak? In this case, we would call this very strong. And so that's what you have to say. You have to state those four things to get full credit for describing the relationship. And in this situation, this is the way I would describe this this relationship. So this is the same graph. And you have to write a paragraph. Okay, you have to write in essence a little paragraph saying this. You have to be complete sentences. You can't just write the words negative, linear, and strong. You have to write it like this, and you have to mention the variables. That's important, with their units, if they have units, okay? And so this would be the proper way of describing this relationship. There is a negative because in general it's going down from left to right. It's not true for every point. Sometimes, it means in general it's going down from left to right. Linear, there's no noticeable curve, and it's a very strong relationship. They are very tightly packed in that pattern. Okay, between and say what your variables are, the mean speed and the gas mileage, there appears to be no outliers. There appears to be no points that are way above or way below the line. So that is really the main part of section 3.1, is being able to draw the scatter plot and be able to describe the relationship with your DOFs situation. And look, getting good at writing this and using proper terminology, I encourage you to look at as many examples as you can and look at the problems in your book with the solutions in the back, and they do a good job of wording things. And that's how you're going to get good at this, by understanding the concepts. The main way you can understand it is by looking at different contexts. All right, in your book, the examples and your problems in your assignment. So that is that. Now, the next thing that's going to help us out is what is known as the correlation coefficient, R. R is a number that tells you how strong it is, because this is a bit of a subjective judgment. When we look at data and we say, oh, that's a really strong relationship. Well, how do you define really strong? All right, and so R is a number that helps us out with that. And R is a number that you don't need to figure out by hand, even though it is on your formula sheet. So it has never been on the AP Stats exam to use this formula, but there is R, known as your correlation coefficient. And it just shows you the direction and strength of your relationship if it's linear. Okay? And I want to go ahead and tell you this from the beginning in regards to R. It does not tell you whether or not data is linear. It tells you whether or not how strong it is and whether it's positive or negative. That's what R is telling you. You have to look at the scatter plot to figure out whether the data is linear, and the residual plot, which that comes in the next section. But so there's the formula for it. And we could talk about this. I mean, it's basically standardizing all your X values, finding the Z-score for your X values, X minus its mean over the standard deviation, and then standardizing the Y values for every point, multiplying them, and then averaging them, adding them up and divide by the number of numbers minus 1. So it is the average of the products of the Z-scores for your X's and Y's. Not really important for you to know that. But what is important is for you to be able to explain what R means. R is either going to be given to you, or you can use your calculator to find it. All right, so and so let me show you how to use your calculator to find it. More often than not, R is given to you, and you have to be able to interpret its meaning. And so that's the main thing I'm going to try to accomplish with this problem. So here's how you find R, and here's the main deal with your calculator that you have to be able to do in this chapter. What we're going to do is we're going to enter this data into our calculator. All right, and so we'll do that into list 1 and list 2. So we're going to do that, we hit our stat button. So we go stat, and then we are going to go edit. So I hit enter on edit. And then I've already entered this data, but you go to list 1, and I entered all of the mean speeds in list 1, and in list 2 I entered in all the gas mileage. So I went ahead and did that beforehand. Now, to figure out what R is, we're going to do this command here. We are going to hit the stat button, we're going to go stat, calculate, and then we're going to go down to the 8th option, linear regression A plus BX, which is really going to be the main deal for next section as well, because it's going to tell us the equation of our line of best fit. But we use that one. We don't use the 4th one, and I'm not going to get into that here. We use this one, the A plus BX, linear regression. So I hit enter. And then my X list, my explanatory variables in list 1, if it didn't say list 1 there, I would put list 1 by hitting second and then the 1 button. Second 1, and that puts list 1 there. And then list 2, now if it didn't say list 2 there, I would do second 2, and it puts list 2 there. All right, now, and this is really something for the next section, but store regression equation, I'm going to have it store it in Y1, and there's a couple of different ways to put it there, but one way is I'm going to store the regression equation in variable Y. So one way to get there is I'm going to hit the vars button. I hit vars and then arrow over Y vars, and then just hit enter, enter, and it puts Y1 there. And so then I hit calculate, and it should tell me R. Now, if your calculator doesn't have R, we're going to talk about that in a second. But there it is. There's my R value. It's negative 0.98 approximately. So our R is equal to negative 0.98. It tells us two things. Now, R is always going to be a number. R is always going to be between -1 and +1 inclusive. Okay? It's always going to go from -1. So it can't be less than -1. It can't be greater than 1. And it tells you how strong your relationship is and whether it's positive or negative. So it says to interpret it in context, you would say, first of all, what's negative? There is a negative. Okay, that's the first thing it said. If this was positive, you would say there's going to be, it is positive. All right, and here's your rule of thumb in regards to R. The closer that R is to, to point, if it's, in general greater than, 0.9, if your R, and really the absolute value of R, if the absolute value of R is greater than 0.9, we call this a very strong relationship. It really depends on your context, and we'll talk about that later. But this is our little rule of thumb. If your R is greater than 0.9 or less than -0.9, we saw that's very strong. If your absolute value of your R is greater than 0.8, all right, we call that a strong relationship. Okay, this is your rule of thumb. It's not some mathematically proven thing, your rule of thumb. And if your R value is greater than 0.7, we call this moderately strong, or a little strong, or marginally strong. So, moderately strong. And anything below 0.7, we would call that weak. It depends on the context. I mean, sometimes there can be contexts where, 0.6 would be something that's great, and we'll talk about that in class. There can be contexts where that can happen. But anyway, so that's our rule of thumb there in regards to R. All right, so in this case, what this is telling you is that there is a negative, very strong relationship, and say the two variables. Relationship, and I'm out of room here, between mean speed in miles per hour, mean speed in miles per hour. One of the most common errors, people leave out the context. It's important that you say the context with the units. Mean speed in miles per hour and gas mileage in miles per gallon. There you go. That's how you interpret R. But it does not tell you, once again, it does not tell you that the data is linear. Okay? You have to determine whether the data is linear or not by looking at the scatter plot and looking at the residual plot, which we're doing in the next section. But you say, oh, it's 0.98. Boy, that's really linear data. No. It's telling you have very strong data. Because truthfully, you could have like exponential data, something that's like this, like an exponential decay function. If you found the R value of that, using our formula or using a calculator, I'm going to guess that's going to be like equal to negative 0.97 or something like that. Very strong. But R is for a linear relationship. Okay, so it really shouldn't be used here with data like this. We would do something, and we'll talk about that later in the year. But anyway, and then lastly, I wanted to talk about some facts about R. These are things that you need to know about R, and your book does a really good job of describing these things, and we'll certainly be talking about this a lot in class. But I've listed 8 things that you should know about R. The first thing is this: is that if we decided to swap our X and Y variables, it would not affect R. So like with this data, if we swap places with all our X's and Y's, they would still be very strongly and negatively related. And so swapping values with your X and Y, it wouldn't affect R. So that's thing one. Changing of units will not change R, and that's been on the exam several times. If you changed, like as opposed to miles per gallon, we went with miles per liter, or as opposed to miles per hour, we went miles per minute. All right, that is not going to affect your R. Okay, it's not going to affect your R. Nor if you standardize the values, means you found all the z-scores for the x's and z-scores for the y's and plotted them. It would not change R, and that's been on the exam before. All right, R has no units. It makes no sense that R is equal to 0.9 seconds. Or R is equal to negative 0.7 miles. It has no units. It is a coefficient. It is your correlation coefficient, and it tells you the direction and strength of a linear relationship. That's what R does. All right. R is always between -1 and 1. The closer to -1 and 1, the stronger relationship. And just to give you an idea, if here's some examples of different R's for different graphs. So like starting with this one, so that's similar to what we just had. That would be an example of data that is it's negative and it is very strong. So that's -0.99. And here, this is positive data, positive 0.9. So we would describe this as positive and very strong. Okay. Now, once again, positive doesn't mean that it's always going up. You know, like between here and here, it's going down. Between there and there, it's going down. It's saying, what's the generality? Positive means it's going up from left to right. So this is negative, but it's not really that strong. This would be -0.7. So we would describe that as a negative relationship, the marginal strength. They're somewhat strong. All right, and then here's an example of 0.5. So, and we don't say a little positive, by the way. Describe it as positive. Okay, it's positive. But you would say there's a weak relationship. Okay, there's a weak and linear relationship. There's no noticeable curve there, by the way. So this is -0.3. That looks pretty randomly scattered. It is negative, but incredibly weak, pretty much randomly scattered. And there's an R of 0. It's just there's really no relationship there. Okay, if you change your X variable, whatever X is, it's not affecting your Y. Let's say X was the amount of medicine that someone takes, and then Y is the amount of virus they have. Well, it doesn't matter how much medicine you take. It doesn't appear to be affecting at all the amount of virus. So that's basically no relationship, no correlation. And of course, if it was equal to exactly to -1, it would be a negative sloping line. Exactly +1, it'd be a positive sloping line. So, and it doesn't now, and it wouldn't matter how steep it is, because that's really sort of how steep it is a function of the units. Okay, if it was a negative sloping line like this, or if it was a negative sloping line like that, that's still going to be, still going to be -1, so to speak, or a positive sloping line in the same way. Okay, so that's examples of that. Correlation does not, we're going to make this point a lot this year. Correlation does not mean causation. I mean, just because things are incredibly strongly correlated doesn't mean that one is causing the other. So we don't use the word cause in a regression setting unless we have what we call a controlled experiment, and that's really a product for next chapter. For instance, if we took these students from different schools and we measured their shoe size, and then we measured their math aptitude, how well they can score on a math test. So their score on some math aptitude test, there would be a very strong and positive relationship. But that doesn't mean that shoe size is causing people to be better at math. It means someone that's in first grade, they're relatively going to have really small feet, and they're not going to do well in the math test because they haven't had any of the stuff yet. Someone in 7th grade is going to have bigger feet, and they're going to score better on the math test because they had more math. And then in 12th grade, their feet are going to be bigger still, and they're going to do better on the math test because they've had 12 years of math. Okay? It doesn't mean that shoe size is causing, and we're going to look at a lot of examples. I don't care how strong your R is. Don't use the word causation or any synonym thereof. Just say that the variables are correlated or they're related. But don't say one is causing a change in the other unless you have a controlled experiment in general. We'll be talking about that a lot. Okay, okay, like we said, both the variables have to be quantitative. You cannot have categorical variables. Number 7, correlation only measures the strength of a linear relationship. Always check the scatter plot to make sure there's not a noticeable curve. And if there is a noticeable curve, we'll deal with that later in the year when we deal with some exponential relationships and power relationships and that sort of thing. But you always have to check your scatter plot and your residual plot like we're going to do next section. So correlation only works for a linear relationship, and you can't check linearity from your R value. And then lastly, correlation is not resistant to outliers or influential points. So for instance, an outlier be way above or below the line. So let's say if we had this data here. All right, and so that R value is going to be really strong, you know, like 0.95 or something. But if we put an outlier on there, that's going to really lower your R value, maybe down to point. But another thing is an influential point. So an influential point is one that differs a lot in the X direction. So let's say if we added a point up here. And so our little model line that we're going to come up with later in the chapter, it's like really close to that. All right, that's going to make your R go through the roof. Okay, it was 0.95, now it's going to be 0.999 or something. On the other hand, if your influential point was way down here, that is like the kid sitting at the end of the seesaw. Okay, it's like someone with a really long lever. It's going to yank that line down to it, and it's going to basically ruin the line for the other points. Okay, and that's going to make your R value go down from like 0.95 to like 0.8. Okay, it's going to really, so that's what we call an influential point. It differs a lot in the X direction. Outliers differ a lot in the Y direction. And so there you go. And so that is your introduction to scatter plots and correlation. Thanks for watching.